How was your mock examination? How was it?
It is fine, ma'am.
It was fine. So uploaded only the undertaking.
Yes, ma'am.
Okay. So you have to, like, your exam begins on Monday. Monday is which paper?
Mathematics.
Yeah.
You got a timetable for that?
Yes.
Yes.
Okay. So Monday is maths, morning 11 to 12.
Yes, ma'am.
And when are you having chemistry?
I think Tuesday.
Tuesday, ma'am.
Tuesday.
Yes, ma'am.
Yes.
Then after Tuesday, what is the next paper subject?
Electrical.
Electrical. That will be on Wednesday. Then Thursday,
CP.
CP. And Friday,
Social science.
social science. And then Saturday, regular
Yeah,
class.
ma'am.
No
Completed.
exam. That means regular class.
Yes, ma'am.
Okay. So things are almost clear for everybody. Now, I would like to know CR. Is CR knowing any student who has left the institute from your section? Roll number 50.
No, ma'am.
No one has left.
No.
Okay. So has 50 joined here? Roll number 50. Are you present? Roll number 40. 40.
Yes, ma'am. Yes, ma'am.
Okay, Ayush, you were not there for the Viva part. Okay, I think we had started and then we had left it. Okay, roll number 50. If anyone gets get to know regarding roll number 50, like he should talk to me. Then roll number 62 didn't write the practical test. So I think you complete your sectional, then we will see who all were absent. So there is no absentee, permanent absentee or cancelled admission or like somehow so because of some reason someone has left the institute. No one is there like this?
No, ma'am.
Okay. So who is the CR in case if anything is like some student finds difficulty during the exam for X section, who can be called directly? The person who finds difficulty? Did you appoint one CR? Who is your CR? Class representative? Roll number 37 is your CR. Okay. I'll mark here. 37 and
37 and 27.
27. Okay. Yeah. Shreya. Shreya is calling me. Yeah. Okay. So we start with the kinetics part, which is remaining. And today I intend to complete your syllabus so that tomorrow can be an off class so that you can read for your exam. Okay. So we started with the introduction and rate law, then how you express the rate law, what is order of reaction and what is molecularity. Then we saw that order and molecularity are two different things. So this is the order of reaction, distinguishing features of molecularity and order. Then we saw a zeroth order reaction. Okay, so there are n number of examples. A common one, if it is asked, you can write those, or you better stick to these PPTs. What all examples are cited in this particular PPT? You can use those examples for writing your uh, answer. Okay. So coming to the next, that is first order kinetics. Now it is very simple thing that you know that the rate of reaction depends on concentration of one of the reactants. So if it is like that, then you call it as first order reaction. So in a first order reaction, the reaction rate is directly proportional to the concentration of one of the reactants. First order reactions often have general form A giving you product. So the rate is written as minus change in the concentration of A, minus because it is decreasing delta T. The rate is equal to K into concentration of A, and the A can be written as the initial concentration of A exponential minus KT, or the test for this particular equation can be written as natural log concentration A is equal to ln A naught is equal to minus KT, which when you plot versus time, you get this is the log A on y axis versus time on the x axis. You get the slope as a negative slope you get, that is minus k value, and the intercept on y axis will give you the log A naught, or the initial concentration. Okay, so that is A is the concentration of analyte A at any time t, and A naught is the concentration of A at time 0, or the initial concentration. So example for this is like the example for first order reaction, the hydrolysis of aspirin and reaction of tertiary butyl bromide with water to give tertiary butanol. Another one is the hydrolysis of anti-cancer drug cisplatin. Now this is the cisplatin, presence of water molecule gives formation of a cisplatin, the first inorganic anti-cancer drug to be. It was discovered. This is the first drug and is unique in its ability to cause complete remission of relatively rare but deadly cancers of the reproductive organs in young adults. So the structure of cisplatin and its hydrolysis product are as follows. Follows, this should be here, and this is the ion form. So the second order reaction. Now there are two type of reaction. One is A plus A giving you product, that is 2A giving you product, or you can have two different reactants, A plus B giving you product. And accordingly, you write the rate equation as rate is equal to minus 1 by 2 dA by dt. So, because that is exactly half. So, you can write the linearized form of the equation as 1 by A concentration is equal to at any time t by 1 by A naught plus KT. Okay, where K is the second order rate constant with units of um, mole inverse per minute, or mole inverse minute inverse. Okay, so this is how you get the graph for such a reaction, such a test of your second order kinetic equation with slope having A into K value. Okay, and for A plus B, you have like the rate constant. Now rate constant with respect to A minus K concentration of A into concentration of B, or you have rate is equal to K A raised to 2. Here that is again for the same type of reactant molecules. So for a second order reaction, T half is given as 1 by K A naught initial concentration of analyte. Okay. So here is the graph of analyte A moles per liter versus time. It goes on decreasing. The number of moles goes on decreasing with the time. Then ln A versus time, and then you have 1 by A concentration at any time t versus time. You see that since it is inverse, you will find that the slope is positive and the K is equal to positive slope. So the examples of reaction, second order reaction are hydrogen ions and hydroxyl ions form water, and then nitrogen dioxide decomposes into nitrogen monoxide and an oxygen molecule is formed along with NO. Hydrogen iodide decomposes into iodine gas and hydrogen gas. Then oxygen O plus O3 ozone, it gives formation of O2. Then NOBr gives NO plus Br2. In the gas phase, nitrosyl bromide decomposes into nitrogen oxide and bromine gas. Then ammonium cyanate in water isomerizes into urea. Hydrolysis of ester. Now, this hydrolysis of ethyl acetate with HCl is a first order reaction, but hydrolysis of ethyl acetate with an alkali is a second order reaction. And these two experiments are demonstrated to students if you come to lab. But now you are not in lab, so I will not take those two experiments. Okay, we will complete it at bomb calorimeter itself in the lab part. Lab today there won't be any lab. Lab will be conducted now after your sessional examination. Okay. Now coming to pseudo first order reaction, it is observed that in certain reactions having two reactants, if one of the reactant present in large excess, its concentration remains practically constant in the course of the reaction, and hence such a reaction will be termed as pseudo first order reaction. So that part is not influencing the rate of reaction. So A plus B giving you product. So rate becomes K prime concentration of A, where K prime is K into concentration of B. Okay. So when B is present in large excess, so it becomes pseudo first order reaction. The actual order is second order, but practically it will be zero order. It will be first order, not zero order. So, sucrose in excess of water gives formation of glucose and fructose. So, excess of water is there, so like it depends on the concentration of sucrose. So, here water is present in large excess, its concentration is practically constant, and rate may be written as rate equal to rate constant K into the concentration of sucrose into the concentration of water, which is equal to K prime concentration of sucrose. So actual order is 2, but experimental order is 1. Hence, such reaction is said to have pseudo first order reaction. Example of reaction that follows pseudo first order kinetics are ethyl acetate in water giving you formation of acetic acid and ethanol. So rate of reaction is equal to rate constant into concentration of ethyl acetate into water. So water is very high, so it becomes only concentration of ethyl acetate. Then hydrolysis of alkyl halides. Alkyl halides, methyl iodide plus water, it gives methanol plus HI or H plus and I minus. So the rate of reaction is a rate constant into concentration of methyl iodide to water. Water is at very high excess, so it becomes the rate is equal to K into methyl iodide concentration. Then summary of zero, first and second order kinetics. For zero order, the rate law is rate equal to K. For first order, rate is equal to K into concentration of A. For second order reaction, rate is equal to K into A raised to 2, raised to the power 2. The concentration time equation becomes A minus A naught equal to minus KT for a zero order reaction, and half-life is T half is equal to concentration of A at zero time or initial time by 2K. For the first order reaction, the equation is ln A minus ln A naught is equal to minus KT. T half is equal to ln 2 by K. Then for the second order reaction, 1 by A minus 1 by initial concentration of A is equal to KT. So T half becomes 1 by K concentration of A naught, initial concentration. Okay, so these are differential rate law, again the same comparison. Integrated rate laws are here written, and these are the straight line graph. And when you plot these straight line graphs, you get some slope value, you get an intercept value, and your equations are here. Okay, so relative rate versus concentration is given here, and half life is uh, T half is equal to concentration, initial concentration by 2K, 0.693 by K for first order reaction, and T half for second order reaction is 1 by K concentration, initial concentration of A. Now the units for rate constant, generally such type of question is asked to compare the half-life and units for rate constant. So this is moles per second, and this is the per second, and this is mole inverse, second inverse, or time inverse. Okay. Then factors that affect the rate of reaction are reaction rate variation is dependent on which substrates are reacting. What is the nature of your reacting for the substrates? Fast reaction include acid reaction and formation of salts and ion exchange. A reaction tends to be slow when covalent bond formation takes place between the molecules and when large molecules are formed. Physical state of the reactant. The physical state solid, liquid, gas of the reactant is also an important factor of the rate of change. When reactants are in same phase, thermal motion brings them into contact. If they are in different phases, the reaction is limited to the interface between reactants, and the reactions can only occur at their area of contact. Vigorous shaking and stirring may be needed to complete the reaction. Then concentration. So if the concentration increases, then the number of collisions or the molecules that must collide in order to react with each other increases. When the concentration of reactant increases, the frequency of the molecules colliding increases, striking each other more frequently. Increasing the amount of one of more reactants causes the collision to happen more often, increasing the rate of reaction due to an increase in number of molecules that have the minimum required energy. Okay, then pressure. Pressure, pressure and concentration are almost like in considered. So for gases, increasing pressure has the same effect as increasing concentration. Increasing the pressure of the reaction involving gas will increase the rate of reaction. With increasing the pressure, its volume will be decreased. Okay, the number of particles remains unchanged. Therefore, increasing pressure increases concentration of the gas and ensures that the gas molecules collide more frequently. PV is equal to nRT. So changing the pressure for a reaction that involves only solids and liquids has no effect on the reaction rate. Then temperature. Temperature is like definitely we know that for every 10-degree rise in temperature, the rate of reaction is either doubled or tripled. Now this is due to increase in number of particles with minimum energy. Okay, given by Arrhenius theory. Presence of catalyst. Substance which hasten the rate of reaction without itself undergoing any change. So the rate of reaction is increased when catalyst provides a different reaction mechanism to occur with lower activation energy. For example, at ordinary condition, H2 gas and O2 gas do not combine at all. However, they do combine in presence of a small quantity of platinum, which acts as catalyst, and the reaction then occurs rapidly. Okay. Then the activation energy. What is activation energy? It is the minimum amount of energy required to initiate a chemical reaction. So this is the potential energy diagram. This is regarding the exothermic reaction. Like suppose A is reacting with B gives C plus D. This is A plus B giving you an activated complex having higher energy, and then it go back to the um, to a stable state where the energy, if the energy is low, then you call this as an exothermic reaction, whereas there can be a case where the product of the reaction has higher energy than the reactants, and we call this as endothermic reaction because the energy is taken up by the system for getting converted into the product. Then reaction rates and temperature, that is the Arrhenius theory. So Arrhenius theory tells you regarding how the reaction rate is influenced by temperature. So K is equal to A exponential minus EA by RT. K is the rate constant, EA is the activation energy, T is the temperature in Kelvin, R is the ideal gas constant 8.314 kilojoules per mole. A is known as frequency or pre-exponential factor. In addition to carrying the units of the rate constant, A relates to the frequency of collision and the orientation of a favorable collision probability. Both A and EA are specific to a given reaction. So Arrhenius gave the thing that molecules must possess a minimum amount of energy to react. Now, why if the question is asked, justify molecules must possess a minimum amount of energy to react, then you can write the answer. In order to form product, bonds must be broken in the reactants, and bond breakage requires energy. Molecules moving too slowly with too little kinetic energy do not react when they collide. The activation energy EA is the minimum energy required to initiate a chemical reaction. EA is specific to a particular reaction. So that is how your activation energy came into the. Now, rate constant. How rate constant? Rate constant is a dependent variable. Temperature is the independent variable. So, as you increase the temperature, your rate constant value will change. And here we find out that K is equal to A exponential minus EA by RT. That is the Arrhenius equation. So, EA is the activation energy, joules per mole. R is the gas constant, 8.314 joules per Kelvin mole. B is the temperature and A is the frequency factor. So ln K is equal to minus EA by R 1 by T plus ln E. Arrhenius noted that reaction rates could be understood to depend on EA and temperature with the exponential form. K is equal to A exponential minus EA by RT, or in logarithm form ln K is equal to ln A minus EA by RT. Using base 10 log to the base 10, log K is equal to log A minus EA by 2.303 RT. So taking two measured values of the rate at two different temperatures, one can write log K1 by log K1 equal to log A minus EA by RT1. Log K2 is equal to log A minus EA by RT2. So log of the second one minus the first one gives you formation of this type. Yeah. And ln k K2 upon K1 is equal to minus EA by R into 1 by T2 minus 1 by T1. So graphically, how it is represented, the Arrhenius equation is graphically represented as your 1 by T reciprocal of temperature and ln k on y-axis, and the intercept on y-axis will give you value of ln a at time t. Yes, and the slope is obtained as minus EA by R. Yes,
Maybe in previous slide there must be plus instead of minus sign. That below formula. ln k2 minus ln k1 is equal to that there must be plus now.
no, this is ln k2 minus k1. You are writing k2 by k1 because it
No,
is
there
log, no? Natural log.
no, 1 by t2 plus 1 by t1 ऐसा होना चाहिए ना
1 by t2 minus 1 by t1.
प्लस होना चाहिए वहां पे क्योंकि बाहर माइनस लिया है ना
This minus this किया है, ये minus value है, हाँ, हाँ, right, बराबर है. You are writing this minus this, so this is already negative. No, but here already negative sign is written. So this minus this minus minus will become plus. Yeah. Okay. So this is how the Arrhenius equation is represented graphically, and the slope value gives you the idea regarding the activation energy by R. R is again a constant, gas constant. So you get the value of your activation energy from the slope, and the intercept on y-axis is obtained from log A at time t. Okay, so then activation energy H2 plus O2 giving you H2O. So activation energy for the forward reaction is given as E transition state minus the E reactants. So here it is seen that the reactants has very high energy, and this is 2 moles of H2 and 1 mole of O2. So that forms the energy of the product is very less. Okay, that is what is represented. Then the activation energy at lower temperature, at higher temperature, and this is the minimum energy required to react. So, like you can calculate the activation energy. The temperature for a system of particles is described by a distribution of energies. At high temperature, more particles have enough energy to go over the barrier. Okay, hence, since the probability of a molecule reacting increases, the rate increases. Okay, so this shaded area, what is shown, is showing the number of molecules with this particular activation energy, and that is why the rate increases. That has been shown. Then consider a reaction N2O plus NO giving you N2 plus NO2. So that is your reactants, if they collide with proper orientation, the transition state is NO bond getting elongated, and your oxygen nitrogen bond keeps forming. So an transition state, or this transition state is forming, and here the EA forward is 209 kilojoules, and EA reverse reaction, for the reverse reaction is 348 kilojoules. So your products has much more stability than the reactant, and because there is decrease in the energy, overall energy, we find that there is a delta H of minus 139 kilojoules. So this minus 139 kilojoules means when these two things react, they will be liberating heat. Okay. Then reaction mechanism. The overall progress of chemical reaction can be represented at the molecular level by a series of simple elementary steps or reaction. The sequence of elementary steps that leads to product formation is the reaction mechanism. Okay. The reaction mechanism for NO gas plus O2 forming NO2, we find that N2O2 is deducted during the reaction. Okay, and the elementary step is NO plus NO forming N2O2, and then N2O2 combining with oxygen forming NO2. Okay, so the overall reaction is twice NO plus O2 giving you twice NO2. Now, what are the reaction intermediates? Now, intermediates
Previous
are
slide, please.
species. Okay. This is a general reaction. Okay, so it is considered that this is occurring in two steps like this. So then we go to find what are the intermediates formed. The intermediates that are formed are species that appear in a reaction mechanism but not in the overall balanced equation. So this is not appearing in the balanced chemical equation. This one overall reaction. So this is your intermediate form. Okay. Okay. Then the rate law and rate determining step. Now, writing possible reaction mechanism, the sum of the elementary steps must give the overall balanced equation for the reaction. The rate determining step should predict the same rate law that is determined experimentally. So the rate determining step is the slowest step in the sequence of steps leading to product formation. Just like your bottleneck, the neck of the bottle is narrow and it will decide how much water at what rate it will be dispensing. So it is something like that. So the reaction mechanism, then you can write a balanced chemical equation is a description of the overall result of the chemical reaction. It can't represent completely the happening of molecular level. The reaction may take place in several steps. A mechanism is devised to explain experimental observation. So this is all experimental. Kinetics is all experimental data. So an important clue in understanding the mechanism of reaction is the rate law. The reason for its importance is once we assume a mechanism, we can predict the rate law. If this prediction does not agree with the experimental rate law, the assumed mechanism must be wrong. Then you assume one mechanism for this. Here, the example considered is twice NO2 gas plus F2 gas, giving you NO2F formation. So here the predicted or assumed rate law is R is equal to the rate constant K into concentration of NO2 raised to 2 and fluorine gas concentration. But the experimental rate law doesn't have this. It depends only on the concentration of NO2 and F2. And let us assume that reaction occurs in a single elementary reaction and NO2 plus F2 plus NO2 giving you this product. So predicted rate law is this. So, however, it does not agree with the experimental value. The experimental value says that it is like this. So, hence the assumed mechanism is discarded. So, you have to discard this particular assumption or assumed mechanism, and it is concluded that reaction occurs in more than one step. So, this has removed the steps. So, the first step is a slow one, NO2 plus F2 forming NO2F plus F. So this F plus the second molecule, this is a fast reaction and hence the rate determining step is this, and therefore the rate becomes K1 because this is the rate of forward reaction for the first step. So the actual mechanism says that it is happening in two steps, the first one being slow and the second one being fast. So the rate of reaction depends on the first slow step, that is given concentration of NO2 into the flow rate. So that is the actual or the experimental, or which goes with the experimental values. The mechanism agrees with the experimental rate law if we equate K1 to K2. Okay. So then, a presence of catalyst, how a catalyst substance that increase the rate of chemical reaction without itself being consumed. So it decreases the activation energy, increases the rate constant. So an uncatalyzed reaction will have very high activation energy, giving you a product C plus D. Whereas for a catalyzed reaction, this activation energy part is the activation energy required is reduced, and that is why the catalyzed reaction occurs at a faster rate. Then the energy diagrams for exothermic and endothermic process. So an exothermic reaction, your reactants are having lesser energy than your products are having lesser energy than your reactants, and this is the delta H, and this delta H is negative. Whereas when you are having the products lesser stability than your reactants, or the energy of your product is lesser than the potential energy is more than the reactants, then you say that it is an endothermic process because this much of energy is consumed during the process. Okay, then collision theory of chemical kinetics. Collision theory used to predict the rate of chemical reactions. For most reactions, for a reaction to take place, the reacting molecules must collide with each other. Once molecules collide, they may react together or they may not, depending on two factors. One is whether the collision has enough kinetic energy to break the bonds holding the reactant molecules together, and the second one, whether the reacting molecules collide in the proper orientation for new bonds to form. So here we see effective collision. So what is an effective collision? For a collision to lead to overcoming the energy barrier, uh, the reacting molecules must have sufficient kinetic energy so that when they collide, the activated complex can form. Now, for this, they should collide with proper sufficient kinetic energy. Then orientation. Now, orientation of molecule, when the two molecules collide in this way, then you get formation of NO plus Cl2 gas. So NOCl plus NOCl, these two gas molecules forming NO plus chlorine gas. So this is ineffective collision where your chlorine atoms are placed or they are, or like in a container there are number of collisions taking place. The collision which is happening because of these two coming close nitrogen, you will find that it is not leading to product formation. This is also ineffective collision, but when the two chlorine are close so that they can form bond between them, and these two parts can separate from it. So chlorine can be removed. The collisions, the effective collisions in which these two conditions are met and therefore lead to reaction are called effective collisions. The higher the frequency of effective collisions, the faster the reaction rate. When two molecules have an effective collision, a temporary high energy, that is an unstable chemical species is formed, and that is termed as activated complex. So according to the collision theory, for an elementary process where the rate law expression is rate equal to K into A into E, so K is PZF. So what is PZF? It can be shown that the fraction of collisions with sufficient energy is F. So fraction of collisions with sufficient activation energy is written as exponential minus EA by RT. E raised to EA by RT. So your R is the gas constant here, T is the temperature in Kelvin. Now P is the proper orientation or orientation factor. Z is the collision frequency factor. So collision frequency factor is written as Z. Then transition state theory. An effective collision between particles lead to formation of a transition state or activated complex. The transition state is an unstable species that contains partial bonds. It is transitional species partway between reactants and product. The transition state cannot be isolated, and the transition state consists at the point of exists at the point of maximum potential energy. The energy required to form the transition state is the activation energy. So
Ma'am,
here
please show the previous slide. Ma'am, previous slide.
PZF, PFZ, and
This one.
PZF or PFZ. Okay, then the transition state theory. Okay, so here what we see, like one is approaching and one is leaving group, and there is a like this particular one which is having highest potential energy. This is termed as activated complex, and this activated complex will be always shown by an dotted line, approaching group and a leaving group. What is written here? Transition state contains partial bonds dashed between C and bromine, carbon and bromine, and between carbon and oxygen. It has a trigonal bipyramidal shape. So depicting the reaction between methyl bromide and hydroxyl ion. Uh, Here the methyl bromide plus hydroxyl ion. How the two are approaching, like the thing is shown here. You can try to understand from the picture shown. So this is the part where the two molecules or the two species are different. The iron part is here and this particular molecule, and they are moving in this. One is moving in this direction, another one is moving in this direction. Then when they approach and lead to formation, there will be a dotted line or a like what you say, um, bond formation or interaction. Okay, electrostatic interaction. So due to this interaction, what happens? The arrangement of the electron pair shifts in such a way that this bond distance of bromine and carbon elongates, and this formation, like it is coming from like a certain distance. Now when it is close to 2 angstrom or 3 angstrom, you will find that it starts interacting with it, influencing this bond also. And the time comes that it stabilizes its energy, and this is having the maximum energy. And then after some time, you will find that the molecule behaves in such a way that this bromine starts moving away from this, uh, leading to a more stable conformation or more stable structure. So that is why, because the stability of this is much more than methyl bromide, methanol, like the removal of bromide, is leading to formation of or having a product which has much lower potential energy than the reactants, and this part is satisfy an exothermic. So here are your reactants before transition state. This is your transition state. This is after transition state, and this is the product form. That's all. So rate constant for transition state theory. Now activated complex or transition state theory. B plus C, like giving you BC, an activated complex, or you call it a star. Then your product is D plus E. So this BC is the activated complex or the transition state. Maximum energy barrier. So rate is equal to Kt by H into the concentration of Bc star, that is the activated complex. So your rate is equal to Kt by H, K, concentration of B to concentration of C, which can also be written as K into concentration of B and C, this B and C. Okay, so your K here is equal to, so first we'll see this part, K is equal to K T by H uh, e raised to minus delta S star by R, that is the entropy of the activated complex, into e raised to minus delta H star upon R, where H is the Planck's constant and K is the Boltzmann's constant. So this is also like, this is all from the thermodynamics. Thermodynamical functions are considered when the transition state theory is explained. So EA, that is the potential energy of activation, the delta H star is the total delta H star is equal to EA minus RT. Okay, so drawing the reaction energy diagrams and transition states. Now, if you are asked to a key reaction in the upper atmosphere is ozone getting converted to O2, and in the stratosphere region, O2 with the oxygen keeps forming ozone. So there is like such type of reaction is taking place there. So you can consider one reaction, that is ozone reacting with nascent oxygen, or oxygen giving you O2 gas. Now the activation energy for the forward reaction is 19 kilojoules, and the DH reaction for the reaction as written is minus, that is DH means delta H is the entropy change for the reaction is minus 392 kilojoules. Okay, so draw the reaction energy diagram, predict a structure for the transition state, and calculate A reversible. So the reaction, so the solution is, the reaction is highly exothermic. Change in enthalpy is minus 392 kilojoule. So the products are much lower in energy than the reactants. So small EA forward 19 kilojoule means that the energy of the reactant lies only slightly below that of the transition state. So the graph will be just like this. Okay, so calculate the value of EA reversible from the value of delta H and EA forward. Predict the transition state structure. Note that one oxygen-oxygen bond of ozone breaks and a new oxygen-oxygen bond is forming. So the solution is delta H is equal to EA forward minus EA reverse. So EA reverse will be equal to EA forward minus delta H for the reaction. So 19 kilojoules minus 392 kilojoules, that is the product. So your EA reverse is 411 kilojoules. So you can draw the diagram in such a way, O3 plus oxygen, this part is 19 kilojoules, but this part is 411 kilojoules, or from here to here it is 392 kilojoules. So you can show the reaction taking place. This is ozone, where the 3O oxygen atoms are moving apart and then leading to formation of O2. Okay. Then coming to numericals, this is another numerical. 3 experiments are run by mixing A and B, data given below. Okay, A and B are mixed in different proportion. One is 1 molar in A and 1 molar in B. The initial rate is given as 1.25 into 10 to the power minus 2. moles per second. Second experiment is run by taking 1 mole of A and 2 moles of B, and you are getting it here. And here you are having 2 moles of this and 2 moles of this. The initial rate is 2.5 into 10 to the power minus 2 moles per second. So what is the order with respect to A? That is 0. What is the order with respect to B? That is 1. And what is the overall order of the reaction? The overall order of the reaction is 1. Then, the rate of decomposition of azomethane was studied by monitoring the partial pressure of the reactant as a function of time. Okay, so determine if the data below support a first order reaction. Calculate the rate constant for the reaction. Okay, so rate constant, if you will calculate, will come out to be this. The more numericals you can try, like a certain reaction proceeds through T, first order kinetics. The half-life of the reaction is 180 seconds. What percent of initial concentration remains after 900 seconds? So you can calculate step 1, determine the magnitude of rate constant K using this. So your K comes out to be like that is 0. This is the first order kinetics. So ln 2 by K or 0.693 by K is your T half. Substitute that in this particular equation. You get K value 0.00385 per second. Then you calculate the time. Okay, so what percentage of the initial concentration remains after 900 seconds? So the percentage of this thing that remains after 900 seconds, to find out that uh, concentration of A at time t by the initial concentration is equal to exponential of minus your K. K value is 0.00385 per second into 900 seconds, that is your KT minus KT. So minus KT, you get this particular 3.12% when you multiply it by 100. Okay. Similarly, you can go for many more such numericals for a second order reaction, and then decomposition of N2o5. This is generally a very favorite question. N2o5 is a favorite because this is the second order reaction, right? So you can just see this where NOBr gives you NO plus Br2 is a second order reaction with respect to NOBr. K is 0.8, okay, per mole per second. So at 10 degrees centigrade. If NOBr is 7.5 into 10 to the power minus 3 molar, how much NOBr will be left after a reaction time of 10 minutes? Okay, so not only this, similar numerical will be definitely there because from the kinetics part, more of numerical questions can be expected. A 2-mark numerical to solve from first order kinetics or second order kinetics or your Arrhenius equation may be asked. Okay, so this is regarding determining the half-life of this reaction first of all, and then you go for determining like half-life only has been determined the half-life of this reaction. So you are asked to calculate the half-life of this reaction. T half comes out to be 160 seconds. Okay. Then first order reactions is the same thing. Yeah, this is the equation. Okay, but numerical is given here. What is the half-life of N2o5 if it decomposes with a rate constant of 5.7 into 10 to the power minus 4? Okay, so from the units you get to know whether it's first order or second order. Okay, Then determine the rate law and calculate the rate constant for the following reaction from the following data. Okay, so you go for this calculation. This is all regarding these things. So your rate constant comes out to be 0.08. You can take a screenshot of this because I'll be closing the class with this numerical. You have some more example. Activation energy of first order reaction is this at 25 degrees centigrade. At what temperature will the rate constant double? Okay. So at what temperature? At 308, it would double. And another reaction, many numericals are here. The reaction 2A giving you B is first order in A with a rate constant of 2.8 into 10 to the power minus 2 per second at 80 degrees centigrade. How long will it take for A to decrease from 0.88 molar to 0.14 molar? So it takes the time taken is 66 seconds. Then the experimental rate law for the reaction between NO2 and carbon monoxide to produce NO and CO2 is a rate equal to K into concentration of NO2 raised to 2. The reaction is believed to occur via two steps. So these are the two steps. So what is the equation for the overall reaction? So the equation for overall reaction is NO2 plus CO giving you NO plus CO2. What is the intermediate catalyst? Intermediate catalyst which is not seen is NO3. NO2 also. So NO2 is seen here. What can you say about relative rates of step 1 and 2? Rate is equal to rate constant K into NO2 raised to 2 is the rate law for the step 1. So step 1 must be slower than step 2. Then proposed mechanism for hydrogen bromide giving you bromine gas. Write the rate law for this reaction. List all intermediates in this reaction and list all catalysts in this reaction. Okay. So this is the rate law. This is the intermediates and there is no catalyst in this particular reaction. Okay. So this completes your syllabus and kinetics part. The absorption and kinetics were a little bit faster, but that you have already studied. You can practice few more numericals from your, if you have any pure chemistry book, you can practice the numericals. So your syllabus is water treatment with definitely a numerical on lime soda process, any numerical on Langmuir or Freundlich, and a numerical on kinetics, first and second order kinetics. Can be or will be there. So that becomes like numericals if it is 3 plus 2 plus 2. So almost 8 marks may be on numerical and some 5 marks kinetics, 3, 4 marks on 3 marks on refractories, 4 marks on adsorption, and rest will be the water treatment theory part. Okay, so that will be your say pattern. Okay, so every one of you should see that you join the WebEx link. I'll be there as the invigilator, and tomorrow we will conduct one MCQ test. Okay, so tomorrow's MCQ test will be informed on first on WhatsApp group, and then when it is scheduled, you will receive an email through which you will solve the MCQ test on these 4 topics. Clear?
At what time, ma'am?
It will be by the WebEx or Google Meet.
No, it is always on your Google Forms. MCQ test will be just like your practical test in Google form.
Video will be by there, ma'am. We have to join by WebEx or
For
Google Meet.
your sessional video will be, you have to turn on the videos. For tomorrow's 10 marks test, you don't have to put on video.
Ma'am, at which time?
Tomorrow is Saturday. Sometime in the afternoon, like 2 to 6, sometime there.
Ma'am, I'm asking about the exam
हाँ,
by WebEx or Google Meet. We have to join. Which one?
हाँ, दो गैजेट के साथ आपको ज्वाइन करना है. एक में वेबएक्स वीडियो ऑन रखना पड़ेगा और एक आप क्वेश्चन पेपर डाउनलोड करेंगे तो आपको क्वेश्चन पेपर एसेस करना पड़ेगा.
Okay.
अगर नहीं है किसी के पास तो let us know that for some time you can see the this thing. क्वेश्चन पेपर को देखने के लिए you can for some time you can switch it off but not always. पूरा टाइम कैमरा बंद नहीं होना चाहिए.
मैम एक क्वेश्चन एक पेज पे लिखना होता है क्या?
नहीं, ऐसा नहीं है. रादर आप जितने कम वर्ड्स में प्रॉपरली उसको लिखेंगे उतना आपका